Am I audible, sir?
Yes, I am audible.
Yes, sir.
The last topic what we have discussed.
Sir, about the isomerisms.
BBT, I think.
Yes, sir. VVT.
The next is CFT. Yes, what the basic application of CFT? Crystal field theory.
Uh, Sir, CFT is crystal field theory. It explains the splitting of d orbital uh, by the ligand. It's assumed that the complexes are ionic in nature. Here, the metal is behave like a positive ions, and the ligands are the negative anions, which come closer. If the d orbitals get splitted into different energy levels. Uh, it can explain basically the splitting of orbitals because of the ligand field.
Yes. According to CFT, why tetrahedral is always high spin? Why is square-planar is always low spin? What the
Hmm.
reason?
Sir, in square planar complexes, the splitting energy is too much high. So the CFSE is higher than the pairing energy. So electrons can pair up in case of square planar complexes, but in tetrahedral complexes, the ligand are generally weak field ligand. They can split it the d orbital less, so less amount of energy is required for the transition. And here also the pairing energy is very much higher than the CFSE, so it cannot pair up or behave as a always high spin complexes.
Yes. What is pairing energy?
The pairing energy is the minimum amount of energy required to pair up electron.
Next is what the formula for tetrahedral octahedral? CFSE formula.
Sir, in octahedral, the splitting is like T2G and EG subcell. Here, the CFSE can be calculated like for T2G, it was 0.4 into the number of electrons plus 0.6 into the number of electrons. And for tetrahedral, the splitting was like that. E and T. Gyrate on gyrate species are not there. Here also the splitting energy CFSE can be calculated by for 0.6 for E cell and 0.4 for T into the number of electrons.
Yes. Yes. What will be the value of octahedral complex in high spin, low spin? D7. D7
Sir,
complex.
D7 complex.
Octahedral complex. High spin and low spin.
Yes,
What will be the value?
sir. In low spin, it was T2G subcell is already filled. That means 6 electrons, 6 into 0.4 minus 2.4 plus 0.4 into 1, 2, sir. 2 delu minus 2 delu for low spin, and for high spin, it was actually I don't have pen paper, otherwise I calculate.
Okay, no problem. Next is John Taylor GTD, John Taylor distortion. Yes, what the basic application of John Taylor distortion? And what the basic difference is static and dynamic John Taylor distortion?
John's Taylor distortion is applicable for mostly the contribute towards most the stability of the complexes. Like in octahedral complexes, something is showing Z out or Z in type of configuration. So based on the John Taylor, according to the John Taylor distortion, the complexes lowers their symmetry to get extra stability, like D9 copper system. Here it shows Z out system. For that, the axial bond are too much longer, so they can elongate it to get the square planar type of geometry and give the extra stability to the complexes.
Yes, what the example of static and dynamic KTD?
Yes, sir. JTD is mostly shown by filling of unsymmetrical EG and T2G subcell. So, sir, dynamic static JTD is shown by D9, D4 type of electronic configurations, but dynamic JTD is for the D6 type of configurations, where it is this type. So,
Yes, good. Next is spinal. Do you have any idea what is spinal? What is spinal?
yes, sir. In spinals, sir, metal ions are present. Metal oxides are present in two state, like +2 or +3, Ab2O type of molecules, sir. There are two types of spinals. One is normal spinal and one is inverse spinal, sir. In normal spinal, the +3 oxidation state of the metal resides on the octahedral voids, and the +2 oxidation state resides on the tetrahedral voids. But in inverse spinal, it was reverse of that. Here, the +2 oxidation state is resides on the tetrahedral, and
Next is what the drawback of CFT?
the CFT explains splitting only, but it cannot explain which ligand is stronger and why it behave like a strong ligand or weak ligand. It just give a spectrochemical series. Based on this, we can say these are strong. So here the splitting is more, but it cannot explain why the ligand is behave like strong and weak.
Yes. Next is LFT MOT, ligand field theory. Yes, what the basic application of ligand field theory?
The ligand field theory state about the mm, LGO formation, ligand group orbital formation. Here the ligand form uh, group, and then they combine with the metal orbital, and uh, mm, then they form complex.
Yes. Sigma bonding octahetal and pi bonding octahetal complex from ligand field theory.
Yes, sir. Sigma bonding orbitals, sigma bonding complexes are forming by the sigma donor ligand, like NS3, S2O. These are the uh, uh, sorry, these are the pi donors ligand, and pi donors are uh, uh, pi ligands are two type. One is pi donors and pi acceptor. Pi acceptors ligands such as carbonyl, cyanides. These are, and sigma donors are halogen groups like chloride, bromide, iodide.
Yes. Next is spectrochemical series. What the basic application of a spectrochemical series and what the role of a spectrochemical series in coordination?
Just depending upon the spectrochemical series, we can get an idea of which ligand is strong ligand, which is weak or moderate. Um, Based on this, we can get the idea of so as this extent of splitting of d orbitals. Like in spectrochemical series, CO, NO, CN are the strong field ligand, which splitted the d orbital more, and like halogens are the weak field ligands, which splitted the d orbital in less extent.
Is what the basic difference spectrochemical series, electrochemical series, and Irwin-Williams series? What are the differences?
Sir, Irwin Williams series is for bioinorganic. Um, it is for the combining capacity of the uh, oxygen, I think.
Irwin,
Uh,
Irwin-Williams series is explain the stability of complex. Yes, no.
yes, sir, yes. Please
Electrochemical
explain
series.
the stability.
Electrochemical series is defined the pi donor, pi acceptor, sigma donor complex in del zero increasing in the order stability.
Yes, sir.
Electrochemical series.
From electrochemical series, we can define the redox potential, sir.
Yes. And next is color and electronic spectra. Yes, which type of transition show is color and electronic spectra in transition element and lanthanide actinide? Describe.
Sir, in transition element, generally DD transition is observed, or something others like charge transfer spectra also we observe in transition element which show color, and in lanthanide actinoids, FF transitions is also there.
Yes, what the selection rule of?
Sir, there are two type of selection rule. One is spin selection rule, one is Laporte selection rule. According to spin selection rule, only those transition are allowed which has delta S is equal to 0. That means same spin to same spin transition is only allowed. But in case of Laporte selection rule, uh, selection of that spectra is allowed, transition of that spectra is allowed where the transition from one symmetry to different symmetry is present, like from gyrate to ungyrate or ungyrate to gyrate.
Yes, good. Next is oracle diagram. What the difference between oracle diagram and Tagano-Sekano diagram?
Yes, sir. In organ diagram, it so explain only about the high spin complexes. These are the only spin allowed transitions. It's so. But in Tanabo-Sunabo diagram, it is for low spin complexes also. Yes, sir.
Next is intense color and faint color. What the basic difference?
Sir, intense color and faint color is due to its color intensity. It depend on the selection rule, sir. If a transition is both Lapote and spin allowed, then the color is more intense or highly intense color. But if it was Lapote forbidden or somehow spin forbidden, then the color intensity is less.
Yes. Next is charge transfer spectra. We talk about charge transfer spectra. What the
Yes,
basic
sir.
application of charge transfer spectra and how many type of charge transfer spectra and what the difference between charge transfer spectra and DD transition? Describe one by one.
The DD transition is the transition from one d orbital to the d orbital, like from T2G cell to EG cell. This type of transition, DD transition are generally forbidden transition, because here the transition can be occurred from G rate to G rate. So these are Lapote forbidden transitions. So these are less intense as compared to charge transfer spectra. But in case of charge transfer spectra, three types of charge transfer spectra. One is ligand to metal charge transfer spectra, another is metal to ligand charge transfer spectra, and intravalence charge transfer spectra. Metal to ligand charge transfer spectra is showing in case where metal is electron rich and ligand is electron deficient. In that type of cases, we observe metal to ligand charge transfer spectra. Here, metal oxidation states are very low, but in case of ligand to metal charge transfer, metal is electron deficient and metal have vacant d orbital to accept the electrons, and ligands have pair of electron to donate. And these charge transfer spectra are both spin and Lapote allowed. So these are highly intense as compared to DD transitions.
Yes, example of inter and intra ligand charge transfer.
Mm.
Ligand to metal charge transfer, metal to ligand, inter and intra. Example.
Yes, sir. I try to recall exact
Ligand
example.
to metal charge transfer KMNO4. Yes, no.
Yes, sir. KMNO4.
Metal to ligand charge transfer is ligand attached to CONO. Yes.
Yes, sir. Electron deficient ligand.
Intervalence charge transfer spectra is example is
Prussian blue.
yes, Prussian blue. And interligand charge transfer example is
Iron compound one.
yes, iron compound कोई नहीं iron compound या Re2Cl8 2 negative MO2Cl8
Yes, sir.
2 negative.
Yes, sir.
Next is magnetism. What is magnetism? The basic application of magnetism. Now, how many type of magnetism? Describe one by one.
Magnetism refers to the response towards the magnetic field. It Magnetism are two type. One is diamagnetic and paramagnetic. based on the electrons, we can say it is diamagnetic or paramagnetic. If there is unpaired electron, then the compound is behave like a paramagnetic. If all electrons are paired, then it can behave like a diamagnetic, and it repel the magnetic field and do not respond to the magnetic field.
Yes, paramagnetic, diamagnetic, antiferro, and ferromagnetic. Yes.
Ferromagnetic. Yes,
Yes.
sir.
For the example,
Sir, paired electronic configuration complexes like the compound having low spin D6 complex. These are uh, efficient 6 4 minus.
yes, paramagnetic, diamagnetic. Ferromagnetic example Fe3O4. Antiferromagnetic
Fe3.
example is nickel oxide.
Yes, sir.
Next is Curie temperature, nail temperature. What the difference?
Sir, I heard about this Curie temperature. Curie temperature is for paramagnetism. I think mm, uh, below this the substance can behave like a paramagnetic, and above this it was behave like diamagnetic. Mm, I can't
No
recall
problem. You
the
look, you
exact
look good.
answer.
You have to study. Next is magnetic moment. What is magnetic moment? Yes, what the magnetic moment for D block and F block element?
Sir, magnetic moment can measure in the Bohr magnetum unit. Um, it can be calculated from the formula, different type of formula for this, like n whole into n plus 2. And for spin orbit coupling, it has different formula for s whole into s plus 1 plus l whole into l plus 1. And but in case of f orbital, we can calculate g factor. Then different type of formula is there, g whole into plus 1 root over. For a block, just one formula we can calculate, but in D block we have to go through that. Is there any spin orbit coupling, or any temperature independent paramagnetism is there, or uh, without orbital contribution is there? Depending on, we can apply different formula and calculate magnetic moment.
Yes, D block element is due to spin only.
No, sir, not only spin only. Orbital contributions are also there,
How?
and temperature independent paramagnetism also.
Yes. And F block element is due to spin plus orbital motion, magnetic moment. The formula of
Yes,
D
sir.
block and F block element.
So for D block, we have different three types of formula. First is n whole into n plus 2. Here we can calculate only spin only magnetic moment. But when orbital contribution is there, here the formula changes, that is root over of 4s whole into s plus 1 plus l whole into l plus 1. This is for orbital contribution. For temperature independent paramagnetism, it can calculate it by um, another type of formula, something lambda by delta 0.
Mu is equal to, देखो, yes, D block is mu s is equal to root n plus 2. D block element.
mm,
And F block is mu is equal to G root J plus 1.
J plus 1.
Yes, how many factor affecting to magnetism? Coordination?
Sir,
Yes.
temperature most accept.
Next is how many types magnetism to determine the magnetic moment?
Uh, Sir, the temperature dependent or temperature independent paramagnetism.
Yes, first is magnetic moment due to unpaired electron. Yes.
Yes, sir.
Second one is ground state term, change to orbital contribution.
Yes, sir. Term symbol.
Yes, term symbol. Triply generate, singly generate, doubly generate.
Hmm.
Third one is perturbation theory. Slightly change in magnetic moment. Fourth one is spin crossover. High spin to low spin, low to
Yes,
high
sir. A spin crossover.
crossover. Yes. Five is free ion complex. LS coupling. Described from the paramagnetic, diamagnetic, antiferromagnetic, and ferromagnetic. Yes, no. Five type of magnetic change to determine the magnetic moment. The coordination
I
chemistry.
read on that.
The next is stability of complex and reaction mechanism. Yes, which type of reaction so thermodynamically stable and kinetically stable?
Kinetically stable.
What the
Sir,
difference?
thermodynamically stable is mostly determined by the uh, uh, it is mainly the thermodynamic parameter up to which it is stable, but in kinetically stable can be explained by two types. One is kinetically labile or kinetically inert. uh, if a compound is kinetically inert, that means it cannot undergo reactions or substitutions reactions. If it is kinetically labile, then it easily undergo substitutions reaction. It doesn't mean that one compound is kinetically labile means it is thermodynamically also uh, unstable. Both are different.
Yes, what the example of reaction? Thermodynamically stable and kinetically stable. Unstable.
Kinetically labile complexes like D high spin D4 complexes, co- CRNS 3 whole 6 2 plus. These are kinetically labile,
Yes.
but it is thermodynamically stable.
Yes, how many factor affecting the stability of complex? Which type of factor affecting?
The nature of the metal, nature of the ligand, surrounding groups. Mm,
Yes, nature of the ligand, chelate ligand, resonance effect, nature of the
Yes,
ligand, macrocyclic effect, steric effect, stirring a.
yes, sir.
Yes, explain. Do you have any idea?
Yes, sir. In nature of the metal, like the metal which has low spin or the metal which are forming inner orbital complex are generally highly inert in nature. The metal having configuration like D3, D8, these are highly inert, and the metal having electronic configuration like D4, D9, these are highly labile in nature. And based on the ligand, like if weak field ligand is there, then the compound is behave like a labile, and the complex behave like a labile. If strong field ligand form complex with the metal, it can form inert complex. And steric effect, if the steric effect increases, then it is easier to substitute the ligand because it's create bulking or it is already bulky. So if it try it always try to lose the ligand to attain the stability, so the ion ligand can easily substituted by another ligand.
Yes. Next one is labile and inert. What the basic difference?
uh, as I said, both of these terms explain the kinetic stability of the complexes. Labile complex are easy to substitute, means easy for the substitutions reactions, and inert complex are less reactive or less prone to the substitutions reactions.
Yes. But the example of Levelian inert complex. Any example?
Yes, sir. Like Levile complex, I give the example of chromium NH3 whole 6 2 plus. It is a Levile complex, and inert complex like D3 configuration, like chromium NH3 whole 6 3 plus.
Yes. Next is associative and dissociative reactions in SN1 reaction mechanism.
Yes, sir. SN1 mechanism proceed through
Associative
two
and
type of
dissociative.
mechanism:
Yes.
associative mechanism or dissociative mechanism. In octahedral complexes, it is hexacoordinated. So it follow mainly dissociative mechanism. In dissociative mechanism, first of all, a leaving group leaves and form a pentacoordinated intermediate, and then the nucleophile attack to the metal center and again form octahedral complexes. In associative mechanism, in generally shown by the square planar complexes, they are four coordinated systems, so they have vacant site to form a or attack nucleophile. So in this mechanism, before leaving the leaving group, the nucleophile attack to the metal center and form the pentacoordinated intermediate, and then the leaving group leaves and again it's regain its symmetry and form square planar complexes.
Next is trans effect. Yes, what are the factors affecting the rate of substitution reaction in the complex, in square planar complex, and other one?
The substitution reaction: bulkiness, nature of the nucleophile, nature of the metal center, steric effect.
Yes, trans effect.
Yes, sir.
Yeah, trans effect. Can you describe trans effect? What is trans effect?
Yes, sir.
Trans effect.
Trans effects. Trans effect tells about the ability of a group or compound to substitutes the group which is present trans to that in a complex. Like CO, if CO carbonyl is present in a complex, and according to the trans effect order, carbonyl have higher trans effect, so it can easily substitute its group which is present trans to each with another group.
Yes, cisplatin and transplatin. What's the basic difference?
Sir, in cisplatin, mm, 2Cl and NH3 are present cis to each other, and in transplatin, both NH3 or Cl are present trans to each other.
Yes, what the basic application of cisplatin?
There, it is most commonly used drug for cancer treatment.
Yes, good. Next is redox reaction.
Yes, sir.
First is basic question related to trans effect. How many theories involved in trans effect?
Sir, mm,
Polarizing theory,
pi
pi bonding theory. Yes,
polarizing theory and pi bonding theory.
yes. What the difference and how it is work in
Sir,
coordinate?
according to polarizing theory, the group which are more polarizable are more strong, so most trans effect, like in or halogen. Like for example, iodide, bromide, chloride. We know that the size of the iodide ion is more and higher, so it can easily polarizable by a metal ion. So it can form strong interaction with the metal. So iodide ion have strong trans effect as compared to other halides. So it can form strong bond and pull its electron density towards the metal, and metal become electron rich, and it easily remove the atom which is present trans to each. And in pi bonding theory, the pi acceptor ligands are from so highest pi high trans effect, because for example CO can form first sigma bond, then it has a vacant orbital, so it can uh, mm, form the metal ion can back donate its electron to the CO, and there is strong interaction between the metal and CO. So the ligand which is attached to the Cl can CO can easily dissociate, and so high trans effect.
Next is redox reaction. What is redox reaction? How many type of redox reaction?
The redox reaction are the reaction in which both the oxidation and reduction taking place in a reaction. Uh, in coordination chemistry, mainly two types of redox reaction. Inner sphere, one redox reaction is proceed through inner sphere mechanism, one is outer sphere electron transfer mechanism.
Yes, inner sphere and outer sphere. Here, one electron transfer and two electron transfer. Which one is?
One electron transfer, sir.
Outer sphere, one sphere. Inner is two electron.
Yes, sir.
Next is photochemical reaction in coordination. Photochemical reaction.
Mhm. So I have not much idea about the photochemical
Okay, no
reactions.
problem. Yes, full chemistry, coordination chemistry. What the basic daily life example of coordination chemistry? First question. And drawback limitation of coordination chemistry.
Sir, coordination chemistry is based on the title, like that. It's the chemistry of the coordination compounds. Basic daily life coordination compound, each like vitamin B12 we intake,
Yes, biological and industrial.
industrial,
Hemoglobin, chlorophyll, vitamin B12, enzyme.
chlorophyll, vitamin B, enzymes.
Yes, and drawback limitation.
Mm, I'm not much aware about this.
Okay, no problem. Drawback limitation.
I'll read on this.
Yes, you look them, you have to study. Basic
sir.
is bonding nature, ligand strength, magnetic properties, color.
Yes, sir.
You does not explain the characteristic color for of coordination compound. Magnetic. Warner and CFT cannot fully explain. So many drawback limitation in coordination chemistry.
Hmm.
Yes, today is sufficient. Next day we will discuss organic and physical and spectrum.
Yes, sir.
Okay, thank you.
Thank you, sir.